This is an experiment number 2A from section A of MBO syllabus. Aim: to find the resistance of a given wire using meter bridge and hence to determine its resistivity or specific resistance. The materials required for this experiment are as shown on the right side, and the circuit diagram is as shown on the left side. The circuit arrangement is made in this way. A resistance box is connected to the left gap of the meter bridge. A wire, whose resistance, R, yet to be determined, is connected to the right gap of the bridge. The jockey is connected to the point, D, on the bridge via the galvanometer. The positive terminal of the battery is connected to point, A, and the negative terminal is connected to point C via the key, K. Theory: meter bridge is a sensitive device used for measuring the unknown resistance. It is based on the principle of Wheatstone's bridge. It consists of 1 meter long wire manganine, or constantan, stretched on 1 meter scale, with 2 gaps in which resistance box P and a wire of unknown resistance R are connected. If P and R be the known and unknown resistances in the 2 caps, and L be the balancing length corresponding to zero deflection of galvanometer, then the working formula is R equals 100 minus L upon L times the known resistance P offered by the resistance box. On the right sides are the steps to be followed while carrying on this experiment. Step 1. Resistance box and wire of unknown resistance R are connected between the left gap and right cap respectively. Remember to make a tight connection, and just like this. Step 2. With 1 ohm taken out from resistance box and with the key K inserted, the jockey is gently touched at both ends of the bridge wire to check the opposite deflection of the galvanometer. When not touched, the galvanometer does not show any deflection, as there is no current flowing through it. When the jockey touches one end of the bridge, the pointer of the galvanometer shows deflection in one direction. When touched at the other end, the pointer shows deflection in the opposite direction. This shows that the meter bridge is working perfectly right. Step 3. With the same 1 ohm taken from the resistance box, a null point, or balancing point, B, is sought for by sliding the jockey gently along the length of the bridge wire. At this point B, the galvanometer shows no deflection. So, point B gives the balancing length AB, which is equal to L, or 35 centimeters. At 35 centimeters, the bridge is said to be balanced. So, when P is 1 ohm, the corresponding balancing length is 35 centimeters. The remaining length is 65 centimeters. When calculated using this formula, we get R as 1.857 ohms. Step 4. The operation is repeated with difference resistances taken from the box. If we take 3 ohms from the resistance box, the balancing length is 59 centimeters, which when calculated gives us the value of R as 2.085 ohms. If we take 5 ohms from the resistance box, the balancing length is 71 centimeters, which when calculated gives us the value of R as 2.042 ohms. Similarly, with 6 ohms taken from the box, the balancing length is 76 centimeters. On the average, the mean value of the unknown resistance, R, is 1.97 ohms. These values are just for the sake of demonstration purpose only. This is just an example of the readings. In your case, it will be different, okay? Next, remove the wire from the bridge and measure its length with a ruler. Write the length of the wire here. Next, use a screw gauge to measure the diameter of the wire, as it was done in class 11. Suppose the length of the wire is 12 centimeters. The least count of screw gauge is 0.001 centimeters. And the diameter is 1.204 centimeters. With all these values, we can now determine the resistivity of the wire.